Hello, my name is Nick Gaskill, and I'm a technical documentation specialist with Wolfram Research. Today, I'm going to be sharing a presentation with you that was originally created by John McLoone, who is our sales and marketing manager in Europe. Over the years, he's collected tips for writing fast Wolfram language code. Often these tips come from the personal experience of debugging one's own code, and also from working with other people's code. So the first thing I'll discuss today is the use of floating point numbers to speed up your computations. And you can see here I say use floating point numbers and use them early. The first two computations here are essentially identical, except for the first one uses integers, while the second one uses floating point numbers. You can tell this difference by the fact that there is a decimal point after the floating point number. So this tells the Wolfram language that it is a floating point number. So computations with exact input, like integers, are much more computationally intensive. And what happens is this causes the first computation to take significantly longer than the second. So you can see here I'm using absolute timing, and the time that it takes the computation to run is the first item in the list, and the result is the second item in the list. Here's another example illustrating the computational difference between exact and floating point numbers. So you can see that when I use the floating point numbers, the second result is much faster than the first. By adding these decimal points after your numbers, you ensure that the Wolfram language will not attempt intensive, high-precision computations. This is the first step towards writing fast Wolfram language code. However, you want to be sure that you don't put too many digits after your decimal point. If you have more than 16, the Wolfram language will just assume that you want a high precision result, and the performance will approach that of if you just use integers or exact quantities. So the next thing I'll talk about is using special data types. One of the advantages of the Wolfram language, at least in most cases, is that it's weakly typed. What this means is that you can write your code and then choose at the last minute whether you want a high precision result or some other type of approximation. This flexibility is great, but there are some special data types to be aware of when you want to make sure your code runs very fast. The first one I'll talk about is packed array. So most of the time, packed array works automatically, provided you use approximate numbers as much as possible. So here, a million element list of random reals is made, and then the amount of memory it takes up is determined. It takes up a little over 8 megabytes, so each number takes up around 8 bytes. Appending one more number should increase the total memory by about another 8 bytes, but instead, as you can see, it nearly triples in total size. So what's going on here? This happens because the initial data set is a large list of real numbers, which automatically triggers the use of packed array. So you can see here I'm using packed array Q to tell if it is a packed array, and it's true. So it is most certainly a packed array. By adding an integer, packed array is no longer in use. So you can see here I've tried the same thing after appending just 1, the integer 1, and it says false, so it's no longer a packed array. The take-home message is not to mix exact and approximate numbers. However, if you're forced to do so, you can use developer toPacked array to force everything to become reals and then pack it. So that's exactly what I've done in this next example. So I've done developer toPacked array after appending the integer. And then you can see it says that it is a packed array. So doing so gives you the expected 8-byte increase in size instead of tripling that you saw earlier. Okay, the next one I'll talk about is sparse array. The sparse array structure is slightly different in that you have to make the conscious choice to use it, and it's also generally less applicable than packed array is. It's really only useful if your data set is comprised of zeros or mostly the same number. A matrix of mostly zeros is created here, with some random values assigned at random positions. Now, the same thing is done here, but with sparse array used instead. The data held by sparse array is much smaller than that of the regular matrix. And this happens because sparse array is only storing the non-zero values, while the regular matrix is storing all the zeros in addition to the non-zero values. So you can see, look at the byte count to determine the size, and when you're using sparse array, it is very much smaller. Operations done in a sparse array also show a significant speed up. So in these next few evaluations, we're doing various matrix operations, and you can see that when we use the sparse data, it is much, much faster. So another type is structured array, but this is preliminary, so I won't go too much into it here, but we're hoping to have it fully up and running in future versions of the Wolfram language. So the next tip I'll talk about for writing fast code is compiling low-level code. Another great thing about the Wolfram language is that you don't usually have to compile anything. You can just type in code and evaluate it as you go. So this is a very flexible way to write code. However, there is a built-in compiler that you might find incredibly useful. The compiler lets you declare types and otherwise optimize your code. The examples here perform the same operation on the same data set. The only difference is that the second one uses compile instead of function. And as you can see, the compile operation makes it significantly faster. You can also add further attributes as options to compile to speed up the operation even more. The ones here make it parallel over a list, which speed things up even more. And yet another thing you can do to make it faster still is send it to the C compiler on your machine. Now this is provided that you have one installed on your machine. So another pretty obvious but powerful tip is to use the built-in functions provided in the Wolfram language. So as a general rule, when there is a built-in function for doing something, you should use it. In other words, use the built-in functions for tasks instead of trying to implement them yourself. So this might seem pretty obvious, but it can make quite a difference. The built-in functions have been optimized for very specific use cases, so they're usually going to be faster than if you were to try to implement them yourself. So I'll just give you a simple example here. Consider this data set of 1 million 2x2 matrices in a list. Say that you want to turn it into a million sets of 4 numbers instead. So you might first think, well, I'm just going to map this over flatten, and this works just fine. It's significantly it's speedy, so you might think, hey, that's great, I'm done. However, this exact use case is already built in with flatten. So that's what this next example shows. What the syntax with the extra arguments in flatten says is to flatten at levels 2 and 3, but leave level 1 alone. So even though mapping to achieve the same thing isn't too terribly slow, this is much, much faster. So I'll give you another example. The do loop in the block here takes a temporary variable and then adds up various fractions. So again, it does perform decently. However, InSum can do the same thing. It was built for this purpose, and as you can see, it is much, much faster. So one thing that you definitely want to be doing, and again, this sounds obvious, but is to understand what your code is doing. And that is much easier said than done. For a simple example, consider this function of calculating the Fibonacci number. So it behaves very badly since it relies on double recursion. However, it is sort of a natural way of thinking about the definition of the Fibonacci number, so you might be inclined to just go ahead and write something like it. So you see, this takes around 15-16 seconds to run, which is not good. So fortunately, the Wolfram language has a built-in function for this that is orders of magnitude faster than the implementation that we wrote there. Doing more than one thing at a time is another thing that you're going to want to think about to speed up your code. So what we're talking about here is parallel computing. So parallelizing your computations can give you significant speed increases, and that much is pretty obvious. However, there are some things that you want to keep in mind regarding parallel computations. For many numerical operations, the Wolfram language will automatically parallelize your code. So after defining data and evaluating the while command, open your activity monitor if you're on a Mac, or task manager if you're on a Windows. and we're going to take a look at the usage of your machine. So my machine is quad core, but it thinks it has 8 cores because each is double threaded. The Wolfram language doesn't make use of dual threading, so my activity monitor reports around 50% utilization of the machine, when in fact nearly 100% is being utilized. So this will run forever if you let it run, or for a very long time, so just go ahead and abort the computation. So then I'll evaluate this next example and do the same thing. I'll open my activity monitor back up, and note that the CPU usage is much lower. And this is because the symbolic computations aren't being parallelized automatically. So that's what was happening in the first one I showed you, is everything was automatically being parallelized. But in this one it's not. So I'll go ahead and abort this one as well, and then talk about this some more. As you might expect, the Wolfram language does provide tools for parallelizing your code. However, as you can see, it's not always a good idea to run everything in parallel. So the first computation here, it's not parallelized, and it takes somewhere around 5 seconds to run. Go ahead and evaluate launch kernels and start up the parallel kernels. So in this case, due to the multi-threading, it thinks it has 8, but it actually only has 4, which I mentioned a little bit about this earlier. What will happen here is that 2 kernels will share each core. Now go ahead and evaluate the same operation as before, but instead of using table, use parallel table. You can see that the operation is much faster. But, as I mentioned, it is not always a good thing to run things in parallel. So in this next example, we use parallel map instead of map. And parallel map is actually slower. And you might think, okay, well, how is that possible? We're distributing things, it should be faster. But this is due to the overhead incurred when sending the data to the parallel kernels. In this case, the data is in the form of many matrices. What happens is that the time it takes to send the matrices to the parallel kernels is actually greater than if you just ran the entire computation on a single kernel. So that is a very important consideration when you're deciding whether you want to make things parallel or not, is to try to think about the data that you're going to be distributing to the kernels and then the overhead incurred as a result of that. So there's a few guidelines that you want to think about before you jump headfirst into parallel computing or using CUDA or other types of GPU computation. So it makes sense that only certain types of tasks actually benefit from being run in parallel. You've already seen the effect of overhead on parallel computations. In other words, the questions and answers have to be small. Otherwise, additional time will be taken to send and receive the answers to and from the parallel kernel. So that's one of the guidelines you want to think of. And then related to this is the fact that tasks also benefit from parallelization when computation is expensive. For instance, you wouldn't want to parallelize a task where the computations being done by the kernels are all trivial. So what would happen in that case is it would lead to most of the time being spent on sending and received data to and from the kernels. So another thing that you want to ensure is that the tasks taken on by the kernels are independent. While there are always ways for the kernels to share intermediate values during computations, there is a time penalty for doing so. So you can think of this in terms of if you're sharing a task with somebody in your office, and they're going to have to wait for your results before they can start what they're doing. So a very similar sort of thing happens when you're trying to share data between kernels. So one of the kernels has to wait for a result to be handed off from one of the other kernels. The end result is, of course, a time penalty. So another case of parallel computing is GPU computing, like CUDA or OpenCL. And this in the last few years has really taken off. Since the powerful graphics cards that are used in GPU computing contain hundreds of processors, the penalties associated with parallel computing in these cases can potentially be very great. So the cases that I've discussed so far where it might take longer to run things in parallel than to just run them on a single core, that can be amplified because GPU computing is massively parallel. So you're going to want to go a step further to ensure that the tasks are both completely dependent and also simple. So you don't want to have hundreds upon hundreds of kernels sitting there waiting for the results from other kernels. So take that case that I mentioned where you're in your office working with somebody waiting for results, and now multiply that times, say, 500. Okay, so things can get out of hand very quickly. You also want to be sure that sending and receiving the data is only done once. Okay, otherwise you're going to spend a lot of computation time distributing the data back and forth, back and forth, back and forth, 500 times or more across hundreds of different kernels. Okay, so that's a basic discussion of the benefits of using parallel computing, and then also some considerations to think of. So I'll go ahead and move on and discuss another point of writing fast code, which is trying to work out things only once. So again, this sounds painfully obvious. So part of trying to do things only once is remembering the values that you've used before. So what you're doing is you're trading memory for performance here. So this is only any good if you've repeatedly used the same values over and over. If you're going to compute something once, and then you're unlikely ever to use the same values again, you're just wasting memory and then also potentially wasting performance. In the case of the really bad Fibonacci that we had earlier, this rescues it because by storing the values that I've calculated once, I prevent that massive recursion. And now if I go ahead and run the fib of 35 that we had before, now it becomes fast. So this is the basic construct that you want to know here, is in the first case I have where I have what the function does in the comment. So use colon equals, and then to say it's a function, but then the first bit of the function is to say that the same pattern again equals, and that way it stores the values as it finds them. So another thing that you want to keep in mind with trying to work out things only once is to watch out with functions that have non-standard evaluation. So plot is a really good example of this. What plot does, and I'll evaluate attributes of plot here, and it will show you its attributes. You can see hold all as an attribute. So what plot does is it holds its arguments instead of evaluating them. So you might just assume, hey, whatever I'm going to put in here is going to be evaluated, but that's not the case with plot. The effect in this example is that it evaluates the integral over and over for each value of n that it's being fed. This ends up taking a very long time. So it's going to sit here and run for a bit, and then you see it comes back somewhere around 10, 11, 12 seconds. So what we can do to prevent this from happening is to force the evaluation inside of plot. So that's what I've done here in the second example by wrapping evaluate around the integral. And as you can see, it's much, much, much faster. So similarly, you can also use with to save and then reuse the result, and you get similar performance gains. So an important thing to remember here is that the same principle applies across many different situations. So I'll do an example here with statistics. So you can see that the second plot command is much faster. So I've done linear model fit, got my fitted model, and then I'm using show to combine the list plot of the data with the mean prediction bands from the fitted model. So the second example is much faster, and that's because evaluate is being used inside of plot to force that evaluation. So another case of strange evaluation is find root. So the first example here is slow, and that's because it's trying to figure out everything symbolically. So remember before I said you want to use floating point numbers because the symbolic calculations, exact calculations, tend to be computationally expensive. So the second example here with find root accomplishes the same thing as the first, but it tells it to only use numerics. So that's why we see a huge increase in the performance. Okay, so another case of trying to work things out only once is when you're doing graphics and trying to build interactive graphics examples. So you want to use dynamic when you're refreshing small parts of graphics. So what exactly does that mean? Well, the example here I have a graphic inside of a manipulate. So this manipulate generates thousands of points. So one of which is red, and we've set it up to where it can be moved with the slider. So note that it's quite slow. So it's really lagging whenever I'm dragging or clicking. And this is happening because every time the slider is moved, all of those thousands upon thousands of points are being regenerated. So this really isn't even necessary because all we're interested in is that one single red point and then moving it. Okay? Um, so what you can do is isolate it by wrapping it in dynamic. All right, and the reason this works is because dynamic works from inner to outer. So for those of you that know more about manipulate, manipulate contains dynamic as part of its internal structure. So by putting another dynamic inside and remembering the fact that dynamic works from inner to outer, what the manipulate will do is first look inside to find any other dynamic structures that need updating. So in this case, what it finds is our red point that has been wrapped in dynamic. So it goes ahead and it updates that, but then nothing else needs updating. Okay, we just want the red point. It sees that and it leaves the rest of the graphic alone. So as you can see here, as I move the slider and click around, it is noticeably faster. There's still some lag, but it's actually usable now. You can move things back and forth and actually track its results reasonably quickly. All right, so another thing to remember when trying to write fast code is to use sow and reap when you're accumulating data. So if you're building a data set, you don't want to use append to for this case. So append to is a very useful function, but it's not very efficient in repetitive cases, like when you're gathering data, building a data set from nothing. And this is because append to does not just tack on a small piece of data to the end of the data set. What it does is it actually regenerates the entire data set when you're just adding one little piece at a time. So as you can see when I run this, it's quite slow. What you want to use instead of append to are sow and reap. Okay, so what happens is sow throws out values and reap collects them all together. And instead of regenerating the whole data set, it's just doing one object at once. And the result is much, much, much faster. All right, so this next one is to go easy on pattern matching. You might think that's counterintuitive or is some sort of argument against the Wolfram language, but that's not the case. Pattern matching is undoubtedly one of the best features of the Wolfram language, but you can definitely get too much of a good thing. So this example that I have is just an implementation of the bubble sort algorithm. What I've used here is triple underscore, and triple underscore means to match anything and everything. And the algorithm looks over and over again, even after it no longer needs to. So in this particular example, once the largest element has been moved to the end, it no longer needs to be looked at. However, because I use triple underscore, it just keeps getting reviewed over and over and over every time it goes through this. So the result is that it's pretty slow. So here I've written a procedural statement which is significantly less readable, but it's much faster. Okay, and then going back to the previous discussion of using built-in functions, what you should really do is use the Wolfram language's built-in sort function, which is even faster still. So the thing to keep in mind here is that even though you may want to use a bunch of pattern matching because it's great and it's easy to use, is if you use too much of it, it can really slow down your programs. Another thing to think about is with scoping constructs. So module, block, and with are the three main localization constructs available in the Wolfram language. So block and with are actually faster than module. And you can see that from these three examples here that module is slower. Block and with have similar performance, which is significantly faster. So this happens because module is creating a new variable each time, whereas block simply suspends the variable temporarily. And because of this, module ends up being a bit slower. So we recommend using block unless you have a very specific reason to use module. It's just kind of a good habit to get into. Okay, so the last thing I'll mention is, and it doesn't sound very helpful, but is to try doing things differently. So that seems pretty obvious and not that helpful, but it's definitely something you want to bear in mind. Mathematica is and the Wolfram language is very complicated, and there are a lot of clever tricks in here, and we're stuffing in new automations all the time. And the end result is that sometimes you'll just run things, and for no apparent reason, something will be faster. Okay, you may run something and it turns out faster, and you don't know why, or it seems like it should actually be slower. So I know that's a very unsatisfying thing, but here's an example which is doing a factorial, and I'm building a loop and multiplying a whole bunch of numbers together, and it takes somewhere around half a second. And here I'm taking a whole bunch of numbers and multiplying them together, and it takes a lot less time. And that's really hard to understand why. You might think it's these assignments in the do loop. But if you actually go through and count the assignments, they account for only about 1% of the time, or even less. So it's not those extra assignments. In fact, it's something called Borwein and Borwein binary splitting, which is when you multiply large numbers of integers together. If you actually split the list in half recursively, and say it's the first half multiplied by the second half, and then subdivide those, you end up with the same number of multiplications. You still end up with however many, in this case we're doing 2 to the 16, so that's a lot of them. And this is the same amount of multiplication, except that you're multiplying the large numbers together less often. So it's a really subtle difference that if you binary split, then you get better performance because of the less amount of time that you're carrying around these 100-digit numbers, because I'm doing this with exact numbers with integers. Now, it's not something that you're going to expect, but our guides have stayed awake late into the night thinking about all these specific cases and things they can implement. And so just because that we've got the whole object together, it's able to use that, but by providing it one number at a time, we're denying it the opportunity to be clever. So the Wolfram language in Mathematica is full of little things like that. And just what you want to do is really just time things and play around with it, sometimes removing things or adding things. Just try different things, and sometimes they work out to be better. So, of course, in this case, you use built-in functions. The factorial function is much better. And as a weirdness, I'll go back to an example that I discussed earlier. When we were putting together the example using the special arguments for flatten instead of mapping that huge list over flatten, strangely enough, partition of flatten is actually faster than the example we had before, where we had that special arguments for flatten. And I have no idea why that is. There's probably some cleverness going on behind the scenes that says flattening the whole thing down to a list and then repackaging it up into sets was faster. So I'm not sure why, but it is. So another thing to keep in mind is that these sort of optimizations, these little tricks that might not make any sense, they can change from version to version, so new clevernesses will come along, so it's definitely something you want to continue doing. So in summary, do not be more accurate than you need to be. All right, you want to use reals, but again, like I mentioned, you don't want to put a huge list of numbers behind your decimal point, because then you'll have a performance penalty as the high precision result is attempted. Other thing is to use the built-in commands, and then also try to use the fewest of them, of your built-in commands. So those built-in functions, like I mentioned before, have been optimized for very specific use cases, and they are almost always going to give you better performance. The other thing is to do things once and also in parallel, where using parallel computing is actually going to give you a benefit, Okay, remember that I discussed some of the drawbacks. You can't just automatically throw everything into parallel and just expect it to be faster. So you definitely want to think about what you're doing, what you're parallelizing before you actually do it. So also remember to compile things. So if you're running a lot of intensive computations, compile them. They're definitely going to be faster. And then last but certainly not least is to experiment. Okay, so that was what I just finished talking about, was that some things may be very unintuitive, that something is just faster for no apparent reason. So, you might try to work things out in multiple ways and time them and see which comes to be the faster. So, I thank you for attending this session, and we'll turn things over to our panel for questions and answers. Thank you very much for your time, and we wish you the best.